You ever wonder what's really going on inside the mind of a machine? I mean, it kind of feels like magic, right? But behind every single decision an AI makes, there's a conversation happening. It's just not happening in a language we speak. And that's the billion-dollar question, isn't it? How do you get from just a bunch of code to something that can recognize your face, translate languages on the fly, or even create stunning art? What is that fundamental spark of learning? Well, here's the secret. It's not magic, it's language. The machine learns to speak a very specific and incredibly powerful language, a language where all the words are just numbers and all the rules, well, they're mathematical theorems. This is the secret language of machine learning. Okay, so let's dive right into this. In this explainer, we're going to pull back the curtain on the mathematics that are the absolute bedrock of modern AI. We're going to try and translate this secret language into something that we can all understand. Think of this language as having three main dialects. First up, you've got linear algebra, which is like the grammar. It gives all the data its structure. Then you have calculus, which is the engine of learning itself. It's what drives improvement. And finally, there's probability, which gives the machine the logic it needs to deal with our messy, uncertain world. So let's start with that first one, the grammar. Before a machine can learn a single thing, it needs a way to organize all the information you throw at it. And that's exactly what linear algebra does. It sets the stage. It creates the world where all the data is going to live. The most basic word in this language is something called a vector. It's really just a list of numbers. That's it. Each number might represent the brightness of a pixel in a photo, or maybe the age and income of a customer. It's how we describe a single thing to a computer in a way it can actually process. Now, if a vector is a single word, then a matrix, well, that's a sentence, or maybe even a whole paragraph. It's just a grid that neatly organizes a whole bunch of those vectors together. So if you've got data on 1,000 customers, you can stack all those vectors up into one big matrix. It's how we represent an entire data set. And this is the really cool part. Once you translate everything into vectors and matrices, whether it's a picture, a song, or a spreadsheet, every single piece of data becomes just a point in a high-dimensional space. That might sound abstract, but trust me, this simple idea is unbelievably powerful. So what can we do with all these points floating in space? Well, look at this. Imagine our complex, messy data is that point labeled V. We can simplify it by finding its shadow on that simpler line, S. That shadow is the closest, best approximation we can get. This is one of the core jobs of machine learning, boiling down super complex data to find the simple, important patterns that are hiding inside. All right, so linear algebra gives us our grammar. The data is all structured and organized. But how does the machine actually learn from it? For that, we're going to need an engine. And that engine is built out of calculus and something called optimization. I mean, that's the whole point, right? A model starts out knowing basically nothing. It makes a guess, and that first guess is almost always going to be wrong. So what's the process for getting less wrong over time? How does it actually get better? The answer is actually beautiful in its simplicity. It gets better by measuring its own mistakes and then just systematically taking steps to make those mistakes smaller. The whole idea is to find the lowest possible error, and this process of minimizing error is the absolute heart of machine learning. But it's not always so easy. This slide illustrates the challenge perfectly. Some problems are what we call convex. They're like the simple bowl you see on the left. No matter where you start, if you just keep going downhill, you're guaranteed to find the bottom. But most real-world problems, they're non-convex, like that crazy mountain range on the right. There are tons of little valleys, which makes finding the absolute lowest point way, way harder. For those nice, simple bowl problems, calculus gives us a fantastic map. This graph shows what we call a cost function. It's just a way of measuring the model's error. Our goal is to find the spot on the bottom axis that gives us the lowest point on the curve. We want to get to the very bottom of this valley of error. So how do we navigate this valley? We use a special tool from calculus called the gradient. And all you really need to know about the gradient is this. It's a pointer that always shows you the direction of the steepest uphill climb. It points which way is up. And here it is. This is the big aha moment. If the gradient points the fastest way up the hill, then what's the fastest way down? It's the exact opposite direction. That's it. Imagine you're on a foggy hill and you just want to get to the bottom. All you have to do is feel the slope beneath your feet and take a small step downhill. Then do it again and again. If you keep doing that, you'll eventually find the bottom of the valley. That whole process, that's called gradient descent. It is the engine of learning. Okay, let's talk about our final dialect. We've got the grammar to structure the data, and we've got the engine to learn from it. But there's a big problem. The real world isn't a perfect, predictable math equation. It's full of noise and randomness and missing pieces. AI needs a way to think about all that uncertainty. I mean, let's be real. The world isn't black and white. It's a world of maybes. A self-driving car can't be 100% sure that shape is a person. A medical AI can't be 100% certain about a diagnosis. They have to live in a world of probablys. And for that, you need the mathematics of probability. And that's exactly what probability provides. It gives the machine a framework to quantify its uncertainty, to put a number on it. It lets it make an educated guess and, crucially, to say how confident it is in that guess. It also gives it a way to update its beliefs as it sees new data, which is just incredibly important. Okay, let's zoom out and bring this all together now. These three dialects, grammar, engine, logic, they aren't separate things. They work together in perfect harmony to create a single, unified language for artificial intelligence. So here's how it all connects. Linear algebra, the grammar, takes messy, real-world info and organizes it into those neat vectors and matrices. Then calculus, the engine, fires up gradient descent to search through that data and find the patterns that minimize errors. And finally, probability provides the logic, letting the whole system deal with uncertainty and make smart judgments in a world that isn't perfect. And that's really the big takeaway here. What looks like magic from the outside isn't magic at all. It's a conversation. It's a dialogue happening between an algorithm and a data set, and it's spoken in the precise, powerful, and kind of beautiful language of mathematics. And what's so amazing is that this language is getting more fluent and more sophisticated every single day, which leaves us with a pretty fascinating final question. As these machines get better and better at speaking their mathematical language, what new ideas, what new discoveries, and what new creations are they going to talk about next?